because my version is a little different at this point. Is it find an equation with a sphere of radius 5? Is that it? Or what?
Find the equation of the vertical plane perpendicular to the y-axis through the point
2, 3, 4? Right there, so it's 14 in mine. Okay. So it says find the equation of the vertical plane perpendicular to the y-axis through the point 2, 3, 4. Perpendicular, so I love this. Perpendicular to the y-axis. Okay, so if we were to draw just our axes right here, like this, you have z, you have y, and you have x. So let's just plot this point here. What's that point? 2, 3, 4? So you do go for a little walk, go out 2, and then you go over how much?
3.
1, 2, 3. And then how far up do you go?
Up 4.
1, 2, 3, 4. So you're sitting like right here, right? So you've gone out 2, you've gone over how much? 3, and you've gone up how much?
4.
4. So you're at this point 2, 3, 4. And the equation of the vertical plane perpendicular to the y-axis. So what is that going to look like? It's going to look something like this, right?
Yep.
It's perpendicular to the y-axis.
Yep. So y equals 3. Y equals 3.
So y is equal to
3.
3. Do we care what x and y equal? No, we don't care what we do not care what x. Y stays the same. It's like remember when we had like horizontal lines? Did it matter what x is equal to for a horizontal line in 2 dimensions?
No, so now planes are like lines.
Yes, exactly.
Okay.
Yes. Direct translation. So for example, if I wanted the plane perpendicular to the z-axis through this point, what would that be?
Z
equals 4. Yeah, exactly. Just because something has a simple answer doesn't mean it's not hard to see. It gets weird. We have to break these down in pieces. Where the sphere intersects each coordinate plane. So let's talk about this for a second. The xy plane. What can you tell me about the xy plane?
It's z equals 0.
Z equals 0. What can you tell me about the yz plane?
X equals 0.
X equals 0. And what can you tell me about the xz plane?
Y equals 0.
Y equals 0. Right, exactly. So if you want to find where two things intersect, you have two sets of constraints. This constraint stays the same. It's all of these points, right? But then what changes? The other constraint. So if you want to talk about where it hits the xy plane, what do you set equal to 0? Z. So you have x minus 1 squared plus y plus 3 squared plus 0 minus 2 squared is equal to 4. That equation is the set of points that satisfies both of those constraints. Can you clean this up a little bit?
Yes.
Yeah, you can clean it up a little bit. And what do you end up with? X minus 1 squared plus y plus 3 squared is equal to what? 0. So you were talking about this before. What does this mean? This is a really complicated way to describe what?
A point.
1 point. Yeah, because how many solutions does this have? Well, hold on. This has x is what? 1. What is y? Negative 3.
Yes.
And z, we already set z was equal to what?
0.
So this is a cool way to describe a single point. So it's tangent, it touches once there. It's kind of cool. So the other three, is it pretty much identical work? Yeah. Is it necessarily going to be 1 point? No, because this right here is the equation of a circle with radius what? 0. So if the radius is anything besides 0, it's going to be a circle and not a point. So we can do it one more time. So if it's x is equal to 0, you're going to end up with 0 minus 1 squared plus y plus 3 squared plus what? What, z minus 2 squared is equal to 4? Was that it? Was it 4? Yeah. So then what do you end up with? You end up with y plus 3 squared plus z minus 2 squared is equal to 3. That's a circle with a radius 3 centered at the point negative 3, 2 on the yz plane. That's it.
The last one's interesting.
Okay, let's do it then. Sure. So that's when y is equal to 0. So we get x minus 1 squared plus 9 plus, z minus 2, I see, equals 4. So what's the problem here?
You have a negative number.
It doesn't touch. It don't touch because positive plus a positive ain't going to be negative. So no touching.
Does this mean that it's...
The definition of L'Hopital's rule makes no reference to the recursive nature of that middle entry, which is like you can keep doing this forever, right? But it implies it by saying until it exists, which is what hung us up a little. Which coordinate? So this is the middle coordinate, right? This is the center of this thing, right? So you have to go up or down. Of course, it has to be a fraction. Yay, right. So how far up are we going?
2.5.
So you go up 2.5, right? So you go up. I'm just going to exaggerate here. You go up 2.5, right? So what? Here's the top of our surface, right? On top of our rectangle. So what is that? That's going to be z is equal to what?
0.5.
A half, right? And then how far down are you going? Another, you're going down 2.5.
-4.
So negative what?
4.
Negative 4.5. So this is one thing you could do. We now know the z coordinates of all the coordinates on the upper part, and we know all the z coordinates of the coordinates on the bottom plane, right? So can you do the similar thing for each of the the x? Sure. And then you look at where they intersect, and then you just pick the colors. Use different colors, and remember, don't go ballistic. It's hard because soon, if I draw too much more in this, it's going to be really hard to decode. Yeah, it is. Let's do one more just to see how nuts it gets. What's the length is going to go the y-axis, right? So what's the length? 13?
6.5.
Come on. Really? Okay, I'm going to go with purple here. So how far over are we going? 6.5, right? So you end up with, oh, that was terrible. That's one thing that's nice about these surfaces is you can sketch really nicely. And so you have this thing, right? So what is this going to be? This is y is equal to what?
6.
Well, no, not 6.5. It's equal to what?
7.
7.5, right? Right? So then you have like this edge right there. And you have this edge right there where it hits. You see what I'm drawing in there? So you have the edges. So then you just need how far on the x-axis you go. And then you go back 6.5. So if you go back 6.5, where are we going to be? Negative 5.5. This is a terrible number. I'm not drawing anymore, okay? I'm done drawing this one. But do you understand the base? This is a definition you've seen before. All it is one added letter. The graph of a function of two variables f is the set of all ordered points x, y, z such that z equals f of x, y. In general, the graph of a function of two variables is a surface in 3 space. This is exactly the same thing as the graph in 2 dimensions, where the graph is the set of all ordered points that make the equation true. There are many different ways to write these. Like you have standard, in 2 dimensions, you have standard form, you have slope-intercept form, you have point-slope form, right? Z equals f of x, y is a really common way to write one type of surface. Is that the only way? No. That's a function, right? There's like a vertical like z-axis test you could make. Are we going to look at surfaces that do all sorts of weird warped things? Absolutely. But to begin with, we need to start you off with something that's a little bit straightforward. So for example, if you wanted to graph a surface, z equals x squared plus y squared. Z equals x squared plus y squared. That's what this says right here. You could make a table like this. So instead of 2 columns, you're going to have your y values and your x values, and then you're going to fill in the grid. And after you fill in the grid, could you theoretically plot a lot of points and then do that? Does it get busy really quickly? Absolutely, it does get busy really quickly. So what do you notice here? This is just the same surface. This is z equals x squared plus y squared right here. What's the only difference between these right here? What's the only difference between these 3? What's the difference?
X, Y, Z.
The size of the little diamonds.
Yeah, the size of the diamonds. Essentially, can you plot more points? So when you looked at that chart before, when I had that chart up there, we bring it up here again, 12.2. This chart breaks it into like integer values, -3, then -2, then -1. Could you make that more dense? You can add in more points. And if you add in more points, what happens to your surface? It becomes more smooth. Exactly. The point is, though, is this something you're ever really going to do by hand? You're not going to plot surfaces, generally speaking. You're never going to plot a surface by plotting a point and plotting another point. You're going to plot other things and connect them with curves, for example, that are going to be a much more effective use of your human time. But there is one thing you can do, which is kind of fun. Wolfram Alpha does 3-dimensional functions really nicely in z equals f of x, y form. So, for example, if you type in right here, z equals x squared plus y squared, it gives you a nice little drawing right here, which is pretty cool. This is the contour diagram for it, and this is what it looks like. It even color codes it for you. It's pretty cool. It's pretty cool. The point is you need to start recognizing what happens when you see certain features of 3-dimensional functions. Certain features of 3-dimensional functions. So for example, let's say we talked about these 3. And we're not actually going to plot any points on these, but I want you to tell me out loud what you can tell me about these 3. So let's take a look at this, for example. So if you knew what f of x equals x squared plus y squared looks like, what's the only thing that's changed here on G? What's the only thing that's changed?
That's going to be the same sort of like paraboloid structure shifted down.
It's a paraboloid shifted down or up.
I think
This is up by how much?
3.
You've taken all the z values and you've shifted up 3. That's it. You've shifted everything up 3. Have you done graphing transformations in other classes before? You know, if y equals x plus 2, you've moved it up 2. What happened here? What does the 5 do?
It's shift 5.
Shift up 5, and then, so this is actually equal to negative x squared plus y squared plus 5, right? So what does that do?
That's an upside down.
Upside down and up 5. Sure. Then it changes more radically. We'll get to that next. So we're looking at small little incremental changes right now, okay? What about this one? What's the only thing that happened here? Shift which direction, how much? Shift how much would shift 1 to the left or right?
Right.
To the right. Is 1 to the right? I'm pretty sure is it 1 to the right? 1 to the right?
Yes.
Because if you move it 1 to the right, it's going to behave like it was 1 to the left. So you've moved it 1 to the right.
Yeah.
Yeah.
How do you explain when you shifted over X?
Oh, like forward and backward. There you go. No, that's it. Wait.
Up,
Shang,
down.
sha, zuo, yo. Like, I don't know what's
Forward and backward.
forward and backwards, forward and back. Qian, ho. Yeah. So, anyway. That's right. Making it even more. Find x. It's right there. Okay. What can you tell me about this surface? So you have z is equal to e to the negative x squared plus y squared. What can you tell me about z? Z is always going to be what?
Decreasing.
Is always what? Be more basic than that. Z is always what?
Positive.
Positive. You know it's always positive, right? E to a power is always positive. What happens to z as x or y or both get to infinity? What happens to z?
Goes to 0.
Z goes to 0. Goes to 0, right? Because what's the limit as, I don't know, let's say limit as q goes to infinity of e to the negative q? It goes to what?
0.
It goes to 0, right? So the point is, as x and y get big, they're being squared. So this can never be, they can never cancel each other out. It can never get small. So it's as you go in a direction. So what's another thing that when you were in calculus land, right? You love calculus, right? I'm AB calculus land, okay? What was one feature of a graph that you like to find? You like to talk about concavity, even more basic than concavity. Max and mins, right? Max and mins. So you know this thing goes down as it goes out on the xy plane, right? The xy plane is the floor. So we might want to find not the lowest point. We know the lowest point is going to be infinitely the highest point, right? Can someone tell me anything about the highest point? What's the highest this thing can go?
It's 1.
Yeah, x and y are 0. The highest is at when x, y are both equal to what? 0. That's going to be e to the negative 0, which is 1. So the highest point is going to be 0, 0, 0, 0, 0, 1. So what does this thing look like? Well, it looks like this thing. Let's take a look at it. So how would you type this in? Let's see if we can type this in here. What is it? E to the negative, right? Oh, look at that. It's already one of the ones that comes up. Cool. Let's see what happens. Ooh, there it is. It's kind of cool.
We would make it more dramatic.
So what's interesting about what Wolfram Alpha shows you, kids, is that it centers. Is it showing you the first octant right there? No, it's not. It's showing you the upper half, because where is the z-axis on this graph? Can someone tell me where the z-axis is?
In the wide part.
Yeah, it's right in the middle, right? So this right here, that is the z-axis. Do you see that, everybody? So then this thing goes down like this, and it comes out. There's the x, and what's this?
Y.
There's the y. Just I want to give you perspective of what you're looking at.
It looks kind of like a 3D bell curve.
Yeah, no, it does. And if you change the perspective, if you change the scale, it becomes a little bit more useful. So the picture they give you in the book, which I didn't clip out here, is a little steeper. But it is. What's kind of cool about it, though, is let's talk about what symmetry does it have. Let's look at that picture. What kind of symmetry do you see? It has like a rotational symmetry to it, right? So basically, any line on the xy plane through the origin, it's symmetric across that. It's kind of cool. Anyway, it's kind of neat. Yeah, it's pretty fun. So play around with Wolfram Alpha. It's neat. The thing you have to be careful of, though, is that you have to enter the function a very specific way. Z equals something x, something y. So sometimes you have to solve. Okay, so the challenge is, what did I say about how we're going to graph these? Are we going to graph points and then connect points in 3 space? That's insanely ugly, right? But do we need to be able to sketch things or have an idea of what something looks like by hand? Yeah. What we're going to look at are cross sections. We're going to look at cross sections. So for example, let me get this in so you can read it while I'm talking about it. What I mean by cross sections are, so we had this, that first surface we looked at was z is equal to x squared plus y squared, right? Z equals x squared plus y squared. Remember that sphere problem where it asked what did it look like or where does it cross certain planes? So keep in mind, like the yz plane, that's when x is equal to 0, right? So one thing we could ask is, what does this look like when it crosses the yz plane? How do you figure out what this looks like when it crosses the yz plane? You set x is equal to 0. So what does this look like? You set it equal to 0 and you get z is equal to what? Y squared. So on the yz plane, what could you draw? Z equals y squared. Could you do that for each of the planes? Does that give you some information about what this looks like? Yeah, so these cross sections are nice. The cross sections that are on the axial planes are really useful. The challenge is these surfaces, can they be bent and warped and really strange? Yeah, absolutely. So what this actually looks like when you start doing cross sections, again, the neater you try to be, the better. So you have z, x, and y. So what did we plug in there? We said x was equal to what? 0, and it was z equals y squared?
Yeah.
Z equals y squared. What does that look like? Z equals y squared.
So is this surface?
It's a parabola, right? It goes through the origin, right? When x is, so when y is 1, what is z? 1. When y is 2, what's z? 4. So it's going to be a parabola that looks like this, right? But that's just on the yz plane, correct? So let's try a different play. Let's try the zx plane. I want to show you what happens here. This is what gets really cool. I don't like saying zx. Why don't I like saying zx? Say xz. Keep it in alphabetical order. So xz plane, that's when y is equal to what? 0, right? So if we do that, what do we end up with? We know that y is equal to 0, so we get z is equal to what? Z is equal to x squared. What's that going to look like? It's a parabola, right? And I'll change colors here. Hold on. Let me change a better color here. Let's use this one. So this color right here, it's going to look like this, right? You kind of see what I'm trying to draw there? I think I did a pretty good job. Does that match what our 3D graph was?
Yes.
We did not have to graph points, but we have a pretty good idea. Now, your tendency is going to be to want to draw more lines, and you could end up sketching a few more. Like maybe, it's going to be something like this. It's like a parabolic bowl, like this. Does that match what our 3D graph gave us? Yeah, absolutely. But Tori, you asked when we were talking about minute changes, what changes did you bring up that you were questioning? So what happens, for example, if you had, this is the big question of the day, it's one of my favorite surfaces, might be my favorite surface. What happens if you had x squared minus y squared? Did we make both negative? No, we didn't. So let's take cross sections instead. So let's say we did the xz plane. That's when y is equal to what? 0. So what cross section is that going to be? Z is equal to x squared. So let's pause for a second and actually sketch that. Z is equal to x squared. It's not that bad. Yeah, you got to be real careful. So this is z, x, and y. And I'll use a different color here. So I'll use red to start off with here. So let's say we did this one as red. So z is equal to x squared. So that's this shape, right? It's on the xz plane. But let's say we wanted to do the yz plane. I like yz. It's gonna be fun. It's gonna be a good time. So let's say we did the yz plane. That's when x is equal to what? 0. So what's that going to be? Z is equal to what? Negative y squared. Can you graph that? Sure. What's that going to look like? So here's a question for you. I brought this up when you first started asking me about three-dimensional space. So this is a surface, right? It's continuous. This is continuous. You can find all the partial derivatives everywhere right there, which is really nice. We haven't talked about that, but you have a basic idea of what that is. Can you tell me what the most interesting point on that surface is?
Center.
The origin. So on the origin, if you're looking from forward to backwards, so on the x-axis, what concavity do you have? Yeah, but then if you look side to side, what is it? This is called a saddle point. And remember how I said in multivariable calculus, some things are going to be a direct translation of two-dimensional calculus. You literally just add plus c squared to the Pythagorean, well, plus d squared to the Pythagorean theorem, and you have the distance formula between 2 points, right? Things get broken here in this instance. Not broken, but it's different. In two-dimensional calculus, can you have two different concavities? No. In three-dimensional calculus, can you? Yes. Absolutely. So this right here is, you want to see what this looks like?
It's kind of analogous to the point infection.
Kinda, yeah. X to the 2 minus, oh there it is, y to the 2. This is kind of cool. You see what the name is right there? This is what it looks like. This is called a hyperbolic paraboloid. This is one of my favorite surfaces in all of math, right here. This is awesome. So look at this. If you're walking this way, you're walking on an upside-down parabola, right? But from side to side, what do you see? Concave up parabolas, right? So at any point here, you have one concavity looking left and right, and you have another concavity if you rotate it 90 degrees, which I think is pretty cool. You see that, huh? It's pretty cool. I can even easier one for you. 2x plus 3y plus 4z is equal to 12. Okay? When x and y are 0, what's z? When you have 0 and 0, what's y going to be? 4. And what do you get? 6, 0, 0. So you know those 3 points are on this plane. How many points do you need to define one plane?
Oh, 3.
3 points. Do we have 3 points?
Yes.
We do. So what can you do? You can plot these 3 points. What do you get? 0, 0, 3. So that's 0, 0, and then 3, right? 0, 4. 4 over here, and then 6. And what do you do with these 3 points? There it is. It extends infinitely in those directions. So you go back over here, you see those functions? What functions have we found? We found the functions for, you see those 3 lines? These, it doesn't quote, there's 1 line, there's 2 lines, there's 3 lines. We found 3 functions that you connect on the planes. You can make a triangle. Oh look, you have a plane all of a sudden. The point is you can reduce these to 3 points or 3 lines. Planes are great. Planes are great. So let's pause here.